Hello, my name is Lukas, Jarron, and I'm a master's student at the Integrated Remote Sensing Studio at the University of British Columbia in Canada. And I'm going to present to you today my research on the detection of sub canopy forest structure using airborne LiDAR. So why do we care about the sub canopy? For starters, the sub canopy influences what the composition of the forest, main canopy, and timber supply of the future is going to look like. The sub canopy also represents the largest component of biodiversity in most forests worldwide. Trees, shrubs, and coarse-woody-debris in the sub canopy are a large part of a forest's fuel load and can influence the severity of forest fires. Some of these intermediate trees can also be ladder fuels, spreading ground fires up into the crown. Our study region for analyzing the sub canopy is located in northern British Columbia, Canada, near the town of Smithers. The area is 48,000 hectares of conifer-dominated forest, surrounded by mountainous terrain and spans multiple climatic zones. Airborne LiDAR was flown in 2016 for this region at a density of 23 points per square meter. The first step in our research was determining what we considered as the sub canopy. This was difficult to find a fixed threshold for height because some stands in the region were quite tall, while some stands were very short. Our solution to this problem was to create a variable canopy height at the stand level based off of Lorey's mean height. So for example, if Lorey's mean height for a stand was 20 meters, we considered the codominant canopy to be 90 to 110% of Lorey's height, while anything above that would be the dominant canopy, and anything 70 to 90% of Lorey's height was the subdominant canopy. These three sections made up the canopy. Anything below this, and still more than 2 meters off the ground, was what we considered the sub canopy. In order to capture the variation within our region, we conducted structurally guided sampling to select our ground plots. We used 3 ALS metrics and evenly broke each one up into 4 unique classes. These included proportion of returns under 2 meters, 95th height percentile, and coefficient of variation. By combining each of the 3 metrics, we were able to summarize the structure of the study area into 14 unique classes, which we did 2 plots per class for a total of 28 plots. This graph shows the variation of the selected plots. On the x-axis, we have the number of sub-canopy trees per plot, and on the y-axis, the canopy base threshold. The red plot has a relatively high base threshold and a large number of sub-canopy trees. This is an example of what this plot looks like. Contrarily, the blue plot has a relatively lower canopy base threshold and a smaller number of sub-canopy trees total. This is an example of what this plot would look like. Once we had all the plots, the next step was to remove the canopy for each to isolate the sub-canopy. Using our previous definition of the canopy, it was then removed to isolate the remaining point cloud that represented the sub-canopy. A suite of ALS metrics were then generated for the sub-canopy point cloud. The resulting metrics were tested through forward stepwise regression to determine the strongest predictor variables that will be selected to make models for sub-canopy basal area, sub-canopy volume, and number of sub-canopy trees. Of the resulting models, the removed canopy model for predicting sub-canopy basal volume performed best with an R-squared of 0.88. This graph displays the improvement over the model where the canopy was not removed. The improvement in the R-squared value was 0.57 improved to 0.88. The removed canopy model for sub-canopy basal area also performed well, with an R-squared of 0.67. This also showed an improvement over the retained canopy model. This image displays the total basal volume for our study region. Using an area-based approach, we apply the sub-canopy volume model to our study area, and it then becomes clear where the more developed sub-canopy is located. The greatest volume of sub-canopy is located here in this region, this belt of dark green. When looking at satellite imagery, this green area seems to be some sort of valley. Future research should focus on why there is more sub-canopy in some regions, such as this valley, and if there is any relationship with certain topographic or ecological variables. These predictive layers for sub-canopy basal area and volume can be used for predicting forest structural stages, wildfire fuel load, optimal areas for selective harvesting, and much more. Thank you for watching, and if you have any questions, please see the contact information provided here.
you.